Spherical coordinates are different in concept from Cartesian coordinates, but if you can represent a position using x, y and z coordinates, then you can represent that same position using theta, phi and radius coordinates, where radius is the radius of a sphere and theta and phi are angles. And you can convert between the two coordinate systems using these formulas. I always use a sphere with a radius of 1, and if you do that, then you can simplify the formulas, and you can think of spherical coordinates then as using only two coordinates, two angles, to represent any position on the surface of a sphere whose radius is 1. So let's talk about what those two angles mean. Let's demonstrate using this sphere. Its radius is 1, and in model coordinates the origin is at its centre. The theta coordinate ranges over 2 pi radians, or 360 degrees, and it controls rotation around the y-axis. And then the phi coordinate ranges over pi radians, or 180 degrees, and it controls rotation relative to the y equals 0 plane, remembering that the local origin is at the centre of this sphere. And you can use the two coordinates in combination to find any position on the surface of the sphere. Spherical coordinates have a number of applications. You can use them to calculate the positions of vertices to generate sphere geometry like this, and they're useful in geography, mapping, astronomy apps. You can use them to pan and tilt the camera, or to rotate an object so that it points toward any point in space. For example, that square there is always oriented so that it faces wherever the camera happens to be. And you can use spherical coordinates to achieve that, as we'll see in a moment. Let's talk about mapping between spherical and Cartesian coordinates. My Cartesian system is right-handed, but I use two slightly different variations of spherical coordinates. One for rotating models in the scene, and one to pan and tilt the camera. Let's start with the model system, which uses these formulas. The indicator's position is the xy position that theta and phi map to. And when theta and phi are both set to 0, you could think of that as the origin of the spherical coordinate system. And that maps to the Cartesian position 0, 0, 1, again relative to the centre of the sphere. And that's the same position that an unrotated model faces toward, like this plane inside the sphere. So it makes sense to calibrate so that the position that a model with 0 rotation faces toward is the same position that you get when theta and phi are 0. That way I can use rotation transforms to orient a model relative to any xyz position. You just take the xyz, convert it to spherical coordinates. From that you'll get a theta and phi where positive theta is positive rotation around the y-axis and positive phi is positive rotation around x. Let's look at some code. So in this example we want to rotate a model so that it faces the camera. You can use the same technique to rotate any model relative to any position in space though. So first we subtract the position of the model from the position of the camera, and that gives us a vector from the model to the camera. That vector could be any length though, so we normalize it next so that it's unit length. And that essentially gives us a position on the surface of a sphere of unit radius around the centre of the model. Then we can just convert that position from Cartesian coordinates to spherical coordinates, and that gives us our theta and our phi. And then we rotate the model by phi radians around x and theta radians around y. and that's the end of the calculation for this particular call of the function. But of course we need to call this function again every time the camera moves. Let's have a quick look in this helper function, the actual conversion. So this function will convert from Cartesian to spherical coordinates. It does it for the model variation or for the camera variation. We'll talk about the camera variation in a moment. But this is the code that goes ahead and does that conversion. The camera system uses slightly different formulas, and the reason for the difference is so that 0, theta and phi map to Cartesian 0, 0, minus 1, which is the position that an unrotated camera looks at. If you imagine a camera at the centre of that sphere looking toward the indicator, at the moment that imaginary camera is looking the same way that we're looking. It's looking into the screen and off into the distance down the negative y axis, and positive theta still causes positive rotation around y, and positive phi causes positive rotation around x. Remember that the camera is at the centre of the sphere, and so positive rotation around x causes it to look up. There's more info on rotation in the previous video. And now, just for a bit of variety, let's change the view to a subjective camera view. So essentially we're just going to teleport ourselves into the centre of that sphere and be the camera that we were pretending was there a moment ago. So this subjective camera view uses the same formulas that we just talked about. And again, positive theta is going to rotate us positively around y, so that pans us to the left, and positive phi is going to rotate us positively around x, and that causes us to look up, or to tilt up. So let's go to the code. The scene base class has this data member, camera spherical coords, and this is its type, which has theta and phi values inside it, and also a flag indicating which of the formulas to use. This is how we construct it. We pass it 0, theta and phi, and this particular flag is called isModel. So if we pass true there, we're saying it's to use the model formulas. If we pass false, we're saying it's to use the camera formulas. And then we update that data member we just looked at inside the pan and tilt camera function, which we pass deltas for pan and tilt into, which of course could be 0, could be any value. And then we update the theta and phi values inside that data member by the appropriate amounts. At this point we have rotated, we've panned and tilted the camera from a spherical coordinate point of view, but now we need to know what position we're pointing at, and we do that in update camera focus position. So the camera focus position is the position at which the camera is looking, and we do that with this helper function that takes this time it's taking the spherical coordinate and it's outputting Cartesian coordinate. So this is essentially the reverse of the conversion we looked at a moment ago. This one's converting from spherical back into Cartesian, and again it's looking inside the argument to see which of the formulas it should use. So let's go back and see how that's used. So now that we have the camera focus position, what do we do with that? Well, we use it in update view matrix. So here's the camera focus position in Cartesian coordinates that we just calculated, and we hand that off to DirectX to do its magic with, to actually create as our look at matrix. And of course, because I always use a radius of 1, that's normalized. That is essentially a normalized vector. So that's it for spherical coordinates.